Okay. All right. So good afternoon. Like I said, so today we are doing the introductory lecture on dose calculations or radiation dosimetry for radiation oncology applications. So I'm going to give you some background information on the Monte Carlo method, and then I'm going to share with you some information on the software itself. And I'll do some illustrations on how you can do a simulation with examples that come with the software. And then maybe you can create your own linear accelerator or treatment machine using the graphical user interface. So let me just share my screen with you. And I hope you can see my screen right now. So what I'm going to do is just to share with you what the Monte Carlo method is about, its applications, and why we use it. And then I'm going to then switch to the virtual mode, and then I'll share with you the actual graphical user interface and how to use it. So let me just save this. So I hope most of you at least have got these icons on their desktop. So you are able to open Beam NRC, right? Simply double click Beam NRC. You should be able to open DOS XYZ, which is the DOS calculation. So Beam NRC is for modeling the treatment head or the radiation unit, like the linear accelerator. And then DOS XYZ is for calculating dose distribution in the phantom or the patient, or whatever medium you have. And then Beam DP is for analyzing the beam that exits the linear accelerator. Right. So, and then EGS is used to generate cross-sectional data, but I'll explain in a little bit more detail. Don't worry too much about these other two if you did install them, the EGS INPRZ and the EGS View. Don't worry about those for now. We'll mostly focus on Beam DP, DOS XYZ, and Beam NRC. We might use the EGS GUI just to show you how you can create some new material that is not already present in the default cross-sectional file, which is the PEGS4, but we'll talk about that. So let's first talk about the Monte Carlo method, right? So in radiation therapy, mostly patients are treated with the linear accelerator, sometimes the cobalt 60, which is based on the radioactive decay of the radioactive source. And for the linear accelerator, the radiation is generated based on accelerating electrons to high kinetic energies. So you can then treat the patient using electrons, or you can direct those electrons onto a target, and then Bremsstrahlung radiation is produced that you are going to use to treat the patient in photon mode, right? And in those two different modes, that is electron versus photon mode, the components of the linear accelerator are a little bit different that are used in order to, for example, if it's an electron mode, then you're gonna need a scattering foil and you don't need a target. And if you are using photon mode, then you remove the scattering foil and you put a flattening field. So they are a little bit different, but are quite similar. So amongst the methods that are used to to calculate the dose distribution in the patient, or the interactions of radiation in the treatment unit itself, Monte Carlo is one of the most accurate, if not the most accurate. And it's been used for many years now. It's initially, when it was used, it had an issue of long calculation times. But with advancements in computer technology and things like variance reduction, we can do an actual real-time patient dose calculation in about 15 minutes. All right. So the application was limited initially, but now Monte Carlo, there is now even treatment planning systems. As you know, the dose that is calculated for radiotherapy treatments has to be determined accurately for the different types of treatments that we do. So we need to know how much dose we are giving the patient to the target and also to organs at risk. So the treatment planning system is usually responsible for that. And these are based on different algorithms. There is a convolution superposition algorithms, there is pencil beam, and there is X-ray voxel Monte Carlo, right? So, which is a form of a sort of a truncated or a condensed Monte Carlo simulation. So they do Monte Carlo simulations, but it's not a full simulation. It's sort of a condensed one, so as to minimize the treatment time or the dose calculation time. So here we are looking at the full Monte Carlo that is used usually for research purposes. And so what I'm giving you here is part of my dissertation that I did for my MSc. So I'm just going to touch on it in terms of the theory and the EGS NRC code system itself and what user codes it contains. All right. So I even given you that introduction, which is sort of why we do this type of thing. And also, by the way, if you are interested in doing research in Monte Carlo, that this will help as an introduction for you to understand the dynamics of how it works. So basically, the reason why we use Monte Carlo, like I said, is because of its accuracy. But not only that, it's also because we can't really calculate the dose analytically. And the geometries that we encounter in real life situations are very complex. So for analytic expressions to work, then we're going to have to simplify the geometry severely and make some serious assumptions. But Monte Carlo, on the other hand, can actually model the dose distribution or the propagation of particles in a faithful manner with accurate representation of the actual geometry. So Monte Carlo itself is based on probability distributions, which govern the individual interactions of particles with matter in order to simulate the individual trajectories. And these trajectories are usually random in nature. So Monte Carlo itself is a statistical process. All right, so it's based on simulating a large quantity of histories or particles in order to get an accurate result. All right. And in contrast to other methods, it tracks an individual particle, right, from the time of its creation to the time until the particle is absorbed or until it escapes from the region of interest, right? And then we can neglect to track or follow that particle. All right. And it's especially useful if we are dealing with a heterogeneous media, which is the case in most practical applications. Like in radiotherapy, the beam encounters bone, soft tissue, lung, air cavities, water, etc. So most media in radiotherapy are heterogeneous in nature. So this is the reason why we use Monte Carlo. So like I said, the concern about processing speed or the dose calculation time has been reduced due to the introduction of better computers and variance reduction techniques. So in terms of why we use it, it's not only because of its accuracy, right, but it's because of its ability to faithfully simulate radiation transport in tissue heterogeneities. Like I said, we not only have lung, bone, soft tissue, and other heterogeneous media, but we also have irregular surface contours, right? So in the radiation oncology class, we do talk about these kind of things. We talk about tissue inhomogeneity. We talk about irregular surface contours, right? And this is usually a problem. And there's several calculation methods that are used to compensate for irregular surface contour, for example. So Monte Carlo gives an accurate distribution of dose around these type of regions. And also sometimes in this heterogeneous media, there's backscatter of dose. So if a beam is propagating and it encounters soft tissue, and then within soft tissue there's bone, at the interface between those two, there tends to be backscattered radiation from bone towards the low density medium. Right. So there's a lot of dose perturbations that occur in the human tissues. On top of that, there could also be prostheses or implants that are artificially inserted into the patient. This would include things like hip augmentation implants, which are usually metallic. Some of them are made of titanium or titanium alloys or cobalt chromium, or sometimes they are polymers of, for example, there's one called ultra high molecular weight, polyethylene. So they come in different materials, shapes, and sizes. So the dose perturbation they cause is quite different from patient to patient. All right. So we can't really put a general assumption on how much the dose is perturbed, right? So particularly if the prosthesis is made of metal, there's going to be considerable hotspots at the interface between the metallic object and tissue. So we need to know how much dose is delivered at different areas within our beam path. All right. And other things that other calculation algorithms struggle with is to simulate dose in steep dose gradients, right? Such as I mentioned, I did mention the interfaces, right? There's also built-up regions, tissue boundaries, even near low density heterogeneities like lung, right? So you can do a Monte Carlo simulation to verify or as a form of a quality assurance technique to verify the dose that the patient actually receives in any given situation. All right, so the technique itself, it works by tracking each and every particle, and it calculates how the particle propagates through any defined geometry according to fundamental principles of radiation physics, right? So Monte Carlo, like I said earlier on, uses probability functions, and these functions are derived from atomic cross sections. What are atomic cross sections? These are basically probabilities, right? So a cross section is a probability that a given a photon is going to interact with a particular material. All right. So if it's a photon, for example, Monte Carlo models all the various interaction mechanisms of photons, right? So if you remember your basic radiation physics, photons interact via photoelectron absorption, right? In which an incident photon is absorbed and then ejects an electron in the process, or via compton scattering, in which a photon sort of transfers some of its energy, not all of it, and then it's scattered in a different direction along with an ejected electron. There's also Rayleigh scattering, in which a photon simply is absorbed and re-emitted with the same energy. So it does not really lose energy, but it changes direction, right? There is also pair production, in which a photon is absorbed, but it emits an electron-positron pair with 0.511 MeV each, right? Then there is photo disintegration, which is basically a high energy. It occurs above 10 MeV usually. And Monte Carlo is very important in that case in terms of modeling the dose deposition, especially by neutrons. So for photo disintegration, which is also called photonuclear reaction, it involves the formation of radioactive products, which pose a risk for the staff, for example. So we want to model how much secondary radiation is produced and how much dose is going to contribute. So Monte Carlo models all of that, and it does that by tracking or by ray tracking each and every particle from the moment of its birth to the moment it loses all its energy, or to the point where it escapes from the region of interest. All right. So it does that through the use of probability density functions that are based on these cross sections or probability of interactions. All right. So these are the different probabilities of different processes that I just mentioned. For example, a photon traveling at a particular energy, is it going to undergo photoelectric absorption, or is it going to undergo compton scatter? What are the relative probabilities of each process happening? So it uses these distributions to compute that. All right. Sometimes both processes can occur with different sort of probabilities. All right. And in order for us to do this accurately, obviously we need to know the accurate geometry. So if we are modeling, let's say, a linear accelerator, then we need to know the geometry of the linear, okay? The distances and the between components relative to each other. We also need to know the materials because radiation interactions depend on the medium, the composition, in other words. If you are modeling on the other end, dose in the patient, so the way you model dose in the patient, you first have to model the radiation unit, and then you store your output at a given point, usually 100 centimeters from the source, right? If it's an SSD technique. And you take that output, you run it through the patient, right? And then you calculate the dose. So for the patient, we also need accurate CT density information, right? So you can actually model an actual human being from actual CT patient data from the clinic. So you simply take those CT slices, you can combine them into a single file, which is in the format compatible with e.g. SNRC or specifically with DOS XYZ. And then you can run your beam from the LINAC through the patient and calculate the dose. All right. And you can calculate now things like PDDs, dose volume histograms, profiles, and other things. All right. So this is sort of a summary of the process. Another very important thing is not only does Monte Carlo faithfully represent the geometry, right? The other thing is Monte Carlo, I did mention it's a statistical process, right? So its accuracy is dependent on the number of events that are called histories that we simulate. So you have to make sure that when you are doing your simulation, in order to keep your statistical uncertainty as low as possible, you must increase this number of particles or histories so that you don't underestimate or overestimate your dose. So this is a very important, but as you begin your simulations, you don't have to use so many histories because they'll also, the more histories you need, the more time it takes to simulate. All right. So you can sort of do and begin with fewer histories, see how long it takes. And of course, that depends on the type of computer you guys are using. So if you have got a weaker computer, you might need to do several simulations. I'll show you how you can do it. And then you can combine the output into one. Or you can just do one simulation with many histories, and then you have to wait. But I recommend that you do that at last if you are sure that everything is correct before you use many of these histories. All right, so the EGS NRC code system itself consists of these. I'm not sure if you can see my screen right now, but I hope so. So the EGS NRC system consists of many codes, some of which I've shown you here, right? But it's not only those. We, however, will focus mostly on beam NRC and for treatment unit simulation and dose XYZ for phantom or patient dose simulation. All right. So the EGS NRC has been used since the early 2000s, and it was tried and tested by several authors. It can simulate both photons and electrons, and can simulate energies from 1 keV up to 10 giga electron volts. So it's quite a versatile software package. And the user codes, I've mentioned beam NRC and DOS XYZ. It also does have DOS, RZ, flu, RZ, CAR-VT, and each of these has got a specific application. But we'll mostly focus on treatment head and dose calculation in this course. There are other codes that are not part of the EGS NRC code system. There's Giant4, there is Penelope, and there is also MCNP. There's also MCNPX, and maybe now there's some later versions, but these are the most popular that I know. There's also one called Topaz, TOPAS. It's also a Monte Carlo software package that is used. Some of them are mostly used for radiation physics calculations, for example, at CERN, Switzerland, where they do have hydrogen colliders and things like that. They do employ some Monte Carlo codes that are more industrial oriented, and they can simulate very high beam energies. So very quickly, beam NRC, like I said, is used to simulate the radiation source, which includes the linear accelerator and cobalt 60 units. It can also simulate low voltage X-rays. So it means it can simulate kilovoltage units that we know as superficial and auto voltage units, right? For example, there are some units that are used for small animal experiments. So for preclinical studies using radiation, you don't want to do your research on a human being. So they do experiments on things like mice or small animals, and they do emit kilovoltage beams. So Monte Carlo is able to simulate those X-ray tubes that are used in clinical practice, or even diagnostic X-ray tubes can be simulated with Monte Carlo with beam NRC. All right. So what it gives you is a 3D model of the radiation unit, right? And it models each and every component using what we call component modules, right? So let me just quickly show you a quick overview of, let me see if I do have, yeah. So this is an illustration, for example, of a linear accelerator, right? So what Monte Carlo does is it uses what we call component modules to model each and every component of the radiation unit. So for example, you do have the target. If you are operating in photon mode, you do have an X-ray target, right? So your electron beams that are accelerated via the waveguide system, right? Remember your radiation oncology. Your electron beams are accelerated to high energies via the waveguide, and then they are directed towards the target through a bending or magnet bending system, right? Through 90 degrees here or 270 degrees. Then they come, they hit the target. Then X-rays are produced via bremsstrahlung and also a bit of characteristic radiation. So you have a target, right? And to model the target, which is simply a block of material, usually tungsten, you use the slabs component module. It's like a subroutine that is used to model, that is customized for a particular geometry or shape. So slabs is good for modeling the target. Constack can be used to model the primary collimator, right? And then flat field would model the flattening filter chamber for the ionization chamber. The ion chamber is used to monitor or to measure the radiation passing through for monitor unit calculations, right? So you need to do monitor unit calculations um, for dose QA, for example. MLCs can be used as well. And these are modeled with MLCQ. There's also another one called MLCE. This depends with the shape of the MLC itself. And then JAWS. JAWS is sometimes called diaphragm. It's basically two sets of blocks. One opens in the X direction, the other one opens in the Y direction. So it can collimate the beam in a rectangular or square shape, whereas the MLC can collimate the beam into any irregular shape, right? So this is like the schematic representation of a linear accelerator, right? So the beam comes through, an electron beam is the target, you get X-rays. It's collimated a little bit by these primary collimators, passes through all these. At the flattening filter, it's flattened into a uniform, profile through the ion chamber and through all these components. So this is what we are modeling with beam NRC. So that's the purpose of beam NRC. It can model a linear accelerator using these component modules, all right? And of course, it can model other units, like I said, cobalt 60, diagnostic X-ray tubes, and other radiation producing equipment. So you see when I show you the actual software that we do have what we call spec modules, which basically specify the name of each component in the linear accelerator. And I'll show you where to store each of those files. All right. So that's how you model a radiation unit. Once you model, you produce what we call phase space files. This will be the output of your simulation, right? And you can choose to store your output at any location that you want in a linear accelerator. So as an example, right, let me just go back um, to that figure that I showed you earlier on. What is it? I think it's here. All right. So you can choose to score your beam here or to score your output here just to see what the beam looks like just soon after the target. You can score your beam just before the collimators, just to analyze your beam and see what it looks like at any position. All right. If you want to do a patient simulation, then you have to score it after the collimators, right? And then you can see what the final beam looks like just before it impinges onto the patient surface. So you are free to score your beam at any location to score your phase space file, which is the output. And then you can analyze that phase space file using BeamDP, right? So BeamDP is what I'm going to talk about now. So we've spoken about beam NRC, used to model the Linux component modules, being the little subroutines that are used to model each and every component of the Linux, and phase space file is the output. So the phase space file itself contains all the information that you need about the radiation beam that is coming out of the Linux. So it gives you things like the position of a particle, its energy, its direction, its charge, right? And a tag, this tag of a particle is usually called a latch. You see that when we open the software, you see things like latch. So charge, whether it's an electron +1 or -1, or a photon 0, or a positron, which is positive, right? Position, type of the particle, its energy, direction, everything for every particle that crosses that scoring plane, right? When you say scoring plane, we are simply talking about where you are collecting your phase space file, all right? Now let's talk about beam DP. Now you have collected your phase space file at whatever location you want. Now you want to analyze that beam, right, or that phase space file. So sometimes you see me use those words interchangeably. So when I say phase space file or just the phase space, I mean the radiation beam itself. All right, so you can use beam DP to analyze the beam. So beam DP is short for beam data processor. So it's basically a beam analyzing software. So you basically input your phase space file and then you can look at different parameters. So if you want to look at, let's say, the spectrum of the beam, what kind of spectrum does it have? You can look at things like what is the angular distribution, energy distribution, scatter plot, fluence, you know, things like that. You can look at different parameters of the phase space file, and this will give you sort of an intuitive idea of what your beam is like, so that you can relate to the dose distribution that you get in the phantom. I'm not going to spend much time on variance reduction, but I'll just mention that it's one of the techniques that was developed to sort of get adequate statistics. As I mentioned earlier on, Monte Carlo is a stochastic or statistical process. So for you to get an accurate dose distribution, you need to have sufficient number of particles or histories. And sometimes you need to use variance reduction methods. This would reduce your statistical uncertainty or your variance, right? Which normally would take a very long time to achieve. Normally, you just achieve a low variance by increasing the number of particles, but that can be very time consuming sometimes. Some simulations can take more than 24 hours, some days, but with variance reduction methods, you are able to run your simulation in a matter of minutes, hours, maybe, depending with how much accuracy you want. So basically, it slightly modifies that faithful simulation of particles to obtain an increase in the precision per unit CPU time. All right. So a simple equation you can use to approximate how much number of particles you should use is this. So if you use n number of particles, then your variance will be given by this equation. All right. So for example, if you use 10,000 histories, then you get 1% uncertainty. In most simulations, we want our uncertainty to be below 2%, but 1% is better. So you can run your simulation using fewer histories, and then you can sort of work out how much particles you need to achieve. If you increase your histories, there is a file that is produced when your simulation is done, which gives you these uncertainties, right? So you can either increase your particles or decrease them in order to achieve this uncertainty, and also looking at how much time it's taking to simulate. Of course, there are other factors that affect the speed, including your computer capabilities and the geometry itself. If it's a complex geometry, you might need a little bit more time. All right, so these are the various methods that are used. For example, range rejection simply stops tracking a particle completely once it's out of the region of interest, or once its energy is too low to cause any significant dose, right? There are others that are used, but I'm not going to spend time on that right now. I'll share this document with you if you want to read it. But another important thing, another variance reduction method is transport cutoff. So this simply deals with basically getting rid of the particle once it's below a certain cutoff energy. For example, if it's a photon, we generally use a p-cut value of 0.01 MeV. All right, so once a photon is below that energy, then we stop tracking it. All right, PEGS 4 is basically a cross-sectional data file Remember, I told you that Monte Carlo is based on probabilities, and these probabilities are based on cross-sectional atomic cross-sectional data. So this data is stored in a PEX4 file, right? So PEX4 file gives you all that information. It's a bunch of numbers. So for example, let's say your photon is being simulated in water, right? So it will give you the density of water, the cross-sectional information on how dose is going to be deposited in water, right? Or the probabilities of a particular interaction occurring in water, all right? So this is the file you use. You see there are two files. One of them is written ICRIU 521. The other one is 700, right? We will talk about this maybe a little bit later. But for the purposes of this course, we will use, or at least for the purposes of the example that I'll show you, we'll use the 700 ICRIU PEX4 data. All right. This is usually used for kilovoltage beams, but we'll talk about that a little bit later. Those XYZ. So now once we're done simulating the whole linear accelerator, we've collected our phase space file, we've analyzed it, we see everything makes sense. We can then input that phase space data into, so the phase space data will be the input into this DOS XYZ. All right. So now we're transporting that beam into the phantom. Let me just show you the geometry of how the whole thing works. So our source here is basically representing the linear accelerator, right? We've modeled it. So this is the geometry for DOS XYZ. I have shown you the geometry for beam, right? You have modeled your beam, right? You've got your source, which AKA the phase space file, right? So your phase space file is considered to be the source now. Now you run your phase space file through into the phantom, right? And of course, the distance from the source to the surface would depend on your technique, whether it's SSD. If it's 100 centimeter SSD, then that would be the distance from your source to the surface. But there's a little bit of a trick there, which I'll share with you. Because now our source is from the phase space file, but this is not the actual source. Remember, the source is the target, right? The focal spot where our electrons create X-rays. That's the actual physical source. But here we are using the term source relative to the phantom, okay? Anyway, so you run through your beam into the phantom. So this is an example of just a simple cubic water tank. All right. Water tanks are usually used in radiotherapy for things like quality assurance, right? Commissioning of the beams, and QA tests. But we can calculate those in water, and we can, of course, calculate other quantities like flatness and symmetry, which are some of the things used in quality assurance of radiation beams. All right. This phantom, you can create it within the DOS XYZ software itself. There is a window that you can use in the graphical user interface to define the voxel sizes and the number of voxels, and then you can sort of build this phantom. And after you execute or run your simulation, then what you get out of this is a 3D DOS file. All right. So you get a 3D DOS file, which is basically a file that consists of all the DOS information in the whole, or let me say within the beam. All right. So all the DOS in the voxels. So for each voxel, there's a DOS value that is assigned to it. So you get this 3D DOS file, and you can then extract profiles from that. You can extract PDDs. You can extract DOS volume histograms if your phantom has been contoured for a particular. Remember, for you to do a DVH, you need to contour that region, right? Whether it's a prostate or PTV, CTV, or organ at risk. you can generate a dose volume histogram if such organ has been contoured. So yeah, like I said before, once you have got your 3D dose, you can extract profiles, you get something like this, then calculate flatness to see if your beam conforms to, for example, manufacturer specifications, right? This could be done during acceptance testing of the equipment itself to see if the specifications of the equipment satisfy the actual performance. All right. And you can calculate the symmetry as well and see if it complies with the specifications, right? You can also perform those calculations in an actual patient based on CT data. So the patient comes in, they are scanned, and there are some DICOM information. Normally, that's the format, but DICOM is not the only one, but it's the most popular. So you can have DICOM CT data, and then what you can do then is to take those CT slices. Remember, the CT scans the patient in slices. So you can sort of take all of those slices and merge them into one using what we call CT create. So I'm just giving you the whole process. We are not really going to do this. I might just give you a phantom which is already processed, and then you can just run the dose through it. But just to show you how it's done, they are slices first. Clinically, they use slices, but for Monte Carlo, you have to simulate those in a single file, which we call XFENT. All right. So it's a phantom file, which is EGS compatible. So you are converting from DICOM CT into EGS compatible phantom file, right? Which is a single file. And then you can run the DOS. And once you do that, you can then end up with a dose distribution that may look like, okay, this is a treatment planning system. I just want to show you. So let's say, this is a 4-field box, all right? And this is what we call MC show. We will use what we call DOS XYZ show. It's basically the same thing with MC show, right? But it basically shows you the isodose lines within a patient. So after you do your simulations, you can just now type in a command on a terminal or on a command prompt. I'll show you how to do it. It's very simple. You simply just have to say show, dose XYZ show, you put the name of your phantom, then you put the name of your dose, and then enter. It gives you something like this. All right, so this was for a prostate treatment. The prostate is shown in red, and we've got 4 beams, one from 0 gantry angle, 90, 180, and 270 gantry angle. All right. So once you do that, then you can plot dose volume histograms for each and every delineated or contoured organ within that region. So this is a DVH, the PTV, and all the organs at risk. In this case, the PTV would be the prostate, right? Plus, of course, some margins. And then the bladder and the rectum would be your organs at risk, right? So you can do all that. I just wanna, in terms of the PDDs, okay, this is the project I did, but you can produce PDDs. I think I do have some of them. Yeah. You can calculate PDDs for different field sizes and different SSDs if you want. And we'll talk about how you can do that within the graphical user interface itself. And of course, you can do profiles, right? Profiles, you can calculate them in either cross plane or in plane. This simply means in the X direction or the Y direction. Or if you want to understand it in different terms, it's either you're calculating your profile in the direction that your MLC is open or perpendicular to that direction. All right. But I think when we do the actual simulation, you understand. All right. So that's it today, where we'll look at our water tank simulation. All right. So this is the type of, let me just rewind back to Beam and RC. This is the type of preview you'll get if you have, once you have defined your linear accelerator, you have input your um, geometry correctly and the material and the distances, and then you say preview, you'll get something like this. This was for an Electra precise linear. Of course, you can simulate different models. We do have got Electra Synergy. We've got a Varian. Now, I think Varian is the one that is used mostly in Trinidad. You can simulate a Varian linear accelerator and preview it like this. You can preview an X-ray tube or whatever radiation unit you are simulating. All right. So that is it on Monte Carlo. Is it making sense, at least in theory? Is it making sense? I know it's a bunch of stuff that I said, but once we start using the interface, it's going to make more sense. So let me now just move on to VirtualBox. All right. I hope you can see my VirtualBox screen before I proceed. Can you see it? All right. Let me actually stop the recording and then I'll record the other part separately. I don't want to have